Right then, so previously we talked about integrals involving some trigonometric functions, and those are important in their own right, just because trigonometric functions are important. But today we're going to talk about something that's actually going to make use of what we discussed in the last lecture. So this one is 7.3, called Trigonometric Substitution. Okay. Now, I just want to warn you, many students find this particular technique of integration difficult. So, if you need to watch the video a few times in order to get it, you need to do a little more practice in order to get it, don't feel ashamed. You're not the first. Anyway, here's how it works. If you are dealing with an integral, and it contains one of the following three expressions, could be something like x squared minus a squared, or x squared plus a squared, or a squared minus x squared, a squared minus x squared, where a is a non-zero real constant, in that case, you can do this technique called trigonometric substitution. Won't always be helpful, of course, but it often can be. The idea is this. We're going to say x is equal to some trigonometric function, and the way that we're going to choose that trigonometric function is going to be rigged so that one of the trigonometric identities will apply, and then that will make the integral simpler. Okay? So here's how it works. If you have the expression x squared minus a squared, and you're wanting to do trigonometric substitution, and what you have to do is you have to say x equals a secant theta for some appropriate theta between 0 and pi over 2, not including pi over 2. If you say x squared plus a squared, then you need to be substituting x equals a tangent theta. And in that case, you need your theta to be between negative pi over 2 and pi over 2 non-inclusive. And then if you have a squared minus x squared, then you want to say x equals a sine theta for theta between negative pi over 2 and pi over 2 inclusive. Okay? Now, in order to really see how this strategy works, we're going to have to do some examples, of course. So, let's get started. I'm going to erase these. I'd recommend writing them down because I'm going to refer to them later. I just don't have more space on the board. So, let's start with this example. We have the integral of dx over x squared times the square root of x squared minus 16. Now then, first of all, let's notice that u substitution is not going to help us here. If you set something like x squared minus 16 to be u, then du ends up being 2x dx, and then you have nowhere to put that extra factor of x, right? And of course, any other selection for u is also going to have similar problems, I think. I don't know for sure, but I can't think of a u substitution that would work for this. Integration by parts, I think would make this even more of a mess. So let's just avoid that. And so we need something new. So this is what we can do here. We can say, all right, well, x squared minus 16, that's the same as x squared minus 4 squared. And 4 is, of course, a real valued constant. So if we want, we can do a trigonometric substitution saying x is equal to 4 times the secant of theta. Okay, and we're choosing secant because it's x squared minus 4 squared. Okay? Now, when we do this, just as in u substitution, we need to take the derivative in order to figure out, well, because we're going to want to put all of this stuff in terms of theta, and so then, therefore, we're going to need the variable that we're integrating with respect to also be theta. So we want a d theta coming out of this somehow. So we'll take the derivative of this. Dx can be written as 4 secant theta tangent theta d theta. And again, that's just notation for saying dx d theta is 4 secant theta tangent theta. Now then, if we do this, then this integral becomes, well, it becomes an integral of 4 secant theta tangent theta divided by, let's see, x squared, so that's going to be 16 times secant squared theta times the square root of, okay, x squared again, so that's 16 secant squared theta minus 16, and of course there's a d theta. Okay? Now, whenever you do a trigonometric substitution, the advantage of that is that trigonometric functions follow a lot of identities. Okay? And when you do these trigonometric substitutions, you are rigging the situation so that the next thing you can do is apply some kind of trigonometric identity. And indeed we can here. Okay? The first thing we've got to do is just factor 16 out of these two terms. So we'll first do that. So we get 4 secant theta tangent theta divided by 16 secant squared theta times the square root of 16 times secant squared theta minus 1 d theta. Now then, secant squared theta minus 1, that happens to be tangent squared theta. So then, in that case, what we're looking at here becomes the integral of 4 secant theta tangent theta divided by 16 secant squared theta times the square root of, well, I suppose this would have to be 16 tangent squared theta d theta. Okay. Now then, square root of 16 is, of course, 4. The square root of tangent squared, you might just think that's tangent. And in this case, you're right. In general, it would not necessarily be tangent, because if tangent is negative, then it would actually just give us the absolute value of tangent. But remember when I showed you those intervals along which we are choosing the theta? Like in this case, for secant, theta had to be between 0 and pi over 2. I got that right? Yes. If you choose theta to be between 0 and pi over 2 as prescribed, then tangent will always happen to be positive. And in that case, it is its own absolute value. So there's absolutely no harm in saying that the square root of tangent squared is just tangent. So this whole thing just becomes the integral of 4 secant theta tangent theta divided by 16 secant squared theta times, okay, I guess that'd have to be 4 tangent theta d theta. And again, strictly speaking, these could have absolute values, but since we're choosing theta like this, it's not going to matter. Okay, so some things cancel. First of all, these 4's cancel from top and bottom. These tangent thetas cancel from top and bottom. And one factor of secant theta cancels from top and bottom, right? So what we get here is, well, first of all, we have 16 left over, so we can just take that out. So we have 1 over 16 times the indefinite integral of, let's see, what's left? Just 1 over secant theta d theta, right? Okay. Now, thankfully, 1 over secant theta, we happen to know a function that that's equal to. It's cosine theta. Okay? So this is just 1 over 16 integral of cosine theta d theta. All right? And so after all this process, this integral has become much, much easier, right? Compared to this. So now, of course, the antiderivative of cosine theta is just sine theta. So this now becomes 1 over 16 sine theta plus c. Now then, just like in U substitution, there's something unsatisfying about this answer, right? Because we had an integral in terms of x, so of course we'd like to find the answer in terms of x as well. But this is in terms of theta. What the hell? Okay? So in order to fix that, we're going to have to figure out what sine theta is in terms of x. Well, so far, the only information we have is that x over 4 is secant theta. I'm pretty sure secant theta is not the same as sine theta, though. So now, what we need to do is we need to figure out a relationship between these two trigonometric functions. And the way we can do that is by just drawing a right triangle. Okay, so I'm going to draw a right triangle, and I'm going to declare that angle to be theta. Now, if secant theta equals x over 4, and it does, because that's how we define things, so secant theta equals x over 4. Well, secant theta we know is 1 over cosine theta, so therefore cosine theta equals 4 over x. Now from here, well, cosine theta, in a right triangle, the cosine refers to the ratio of the adjacent side to the hypotenuse. So, what this is telling us is that there is a triangle out there with an acute angle of theta whose adjacent side is 4, and whose hypotenuse is x. So, 4 and x can go on this diagram. Now from here, well, what we are really after is sine theta. Sine theta we know is opposite over hypotenuse, but we don't have the opposite. But that's no problem, because just like in high school, if you have two sides of a right triangle, then you can always just use the Pythagorean theorem to find the length of the third side. So, the Pythagorean theorem indicates that this third side is going to be, well, it's going to have a length of the square root of x squared minus 4 squared, and of course 4 squared is 16. Okay, so what we get from this is that sine theta has to be, let's see, opposite over hypotenuse, so that would be square root of x squared minus 16 divided by x. And with that, what we are looking at here becomes, well, this indefinite integral becomes the square root of x squared minus 16 divided by 16x plus c. And that That is our answer. Okay? And this is always how it goes, right? You see an integral that involves x squared minus a squared, or a squared minus x squared, or x squared plus a squared. You make a substitution involving a trigonometric function. It's either sine, tangent, or secant. It's never the other three. It's only sine, tangent, and secant. And you go through what that implies, and hopefully your integral ends up being a lot simpler. Okay? And then from there, you just need to turn things back into terms of x, which is what this triangle diagram is for. So, let's take a look at another example, because, of course, I'm not going to just leave you with one. This is, I'd say, the hardest of the methods of integration that we're going to learn in this class. Yeah, I'd say this one is probably the hardest. At least for most people. So let's look at the square root of 4 minus x squared dx and try to find its indefinite integral. All right, well, if you want to do that, once again, U substitution isn't going to get you anywhere. Integration by parts, it might work, but I'm not sure. I mean, it wouldn't be impossible for there to be more than one way to do the integral. Integration by parts might actually work here, not sure. But in any case, what we're going to try to do this time is we're going to try to do this by a trigonometric substitution. So, since this looks like a squared minus x squared, right, because we can say that 4 is 2 squared, we're going to make the substitution x equals 2 times the sine of theta. In that case, dx is going to have to be 2 cosine theta, d theta. Right? So that means that what we're looking at here can be written as the integral of the square root of 4 minus, let's see, x squared is going to end up being 4 sine squared theta. And then dx is 2 cosine theta d theta. Okay? Now, always, when you're doing a trigonometric substitution, your next step after just defining x and putting everything in is to get the trigonometric identity to work out. It's always going to be either sine squared plus cosine squared equals 1, or secant squared minus tangent squared equals 1. It's always going to be one of those two. In this case, I look at this and I say, all right, well, if we factor out 4, we get 4 times 1 minus sine squared, which is cosine squared. So this is the same as the integral of the square root of 4 times 1 minus sine squared theta times 2 cosine theta d theta. Now from here, like I said, 1 minus sine squared is cosine squared, so we can go ahead and put that in. So this becomes the integral of the square root of 4 cosine squared theta times 2 cosine theta d theta. So then you take the square root of 4, the square root of 4 is 2, and the square root of cosine squared theta, and strictly speaking, that's just the absolute value of cosine theta. But again, we have chosen theta to be in a specific range. In the case of the sine substitution, we chose theta to be between negative pi over 2 and pi over 2. That means that cosine is going to be positive, right? Because cosine is positive over this whole range. So that means that it is its own absolute value, So there's no harm in just saying that the square root and the square cancel each other again. Okay? So what we get here is the integral of 2 times the cosine of theta times 2 times the cosine of theta d theta. I'm just going to take out those 2's and put together the cosines, so we get 4 cosine squared theta d theta. Okay? Now this one, we can't handle this. We can't handle this because cosine squared, we have an identity for turning that into just cosine of something. We know that cosine squared theta is the same as 1/2 1 plus the sine, no, 1 plus the cosine of 2 theta. So this is 1/2 1 plus cosine of 2 theta d theta. Now, of course, the 1/2 and the 2 multiply to give us 2. So we get 2 times the integral of 1 plus the cosine of 2 theta d theta. So then, of course, antiderivative of 1 is just theta. And antiderivative of cosine of 2 theta is 1/2 sine of 2 theta. And then there's a plus c. Okay. And again, the cosine of 2 theta, you can figure out its antiderivative by doing a u substitution. Personally, I can just do it in my head. At this point, I always know it's just going to divide by the coefficient on theta. But yeah, that's how you would do it formally. Also, if you're wondering why the c is outside and not inside, it's because it doesn't matter. Whether it's c or 2c, it's just a constant, so who cares? Okay, so now next up, once again, there's something unsatisfying about this answer because it's not in terms of the original variables. So in order to figure it out in terms of x, we're going to once again draw a right triangle and figure out a relationship between sine of 2 theta and x. Sine of 2 theta is definitely not 2 sine theta, by the way, okay? Just to be clear about that. Right then, so if we draw a right triangle, we're told that x is 2 sine theta. So that means that if we have theta here, and sine is opposite over hypotenuse, then there's a right triangle out there whose opposite side is whose opposite side is x, and whose hypotenuse is 2. Okay? And then from here, the Pythagorean theorem indicates that this other leg has to be 4 minus x squared's square root. Now, at first, that doesn't seem to help us with sine of 2 theta, right? You look at this and you're like, okay, this is about sine of theta, but sine of 2 theta is completely different, right? Yes, it is. But we have a trigonometric identity for this one too, right? We know that sine of 2 theta is the same as 2 sine theta cosine theta. Okay? And then sine theta, well, we already know that's x over 2. So this is 2 theta plus 2 times x over 2. And then cosine theta, we know that's going to be adjacent over hypotenuse. So that's going to be square root of 4 minus x squared over 2. Okay? And that's almost completely done. The only thing that's missing is this other theta, right? And if you think about that for a second, you realize this triangle isn't really going to help with that, right? This triangle can tell you all about the trigonometric function's values at theta, but theta itself is a little bit harder to reach, right? in this case, there's really nothing you can do in order to write this as something nice in terms of x. The only thing you can do here is say x over 2 equals sine theta, so therefore theta is going to be arc sine of x over 2. So this is 2 arc sine of x over 2 plus x times square root of 4 minus x squared divided by 2 plus c, and that is our indefinite integral. Okay? And by the way, the arc sine of x over 2 really is, well, the sine of the arc sine of x over 2 really is x over 2. That's always true. The problem is when you have the arc sine of the sine of something. That's not always the original. Think about it, it's not really important in this case. The point is, there's not much you can do about theta except write it as arc sine of x over 2. And sometimes that's the case. When you get theta just hanging out by itself with no trigonometric functions acting on it, that's pretty much all you can do. Okay, so let's do another example. Next up is the integral of 1 over the square root of x squared plus 9 dx. So once again, u substitution isn't going to help you here. This isn't the derivative of a function you know. And integration by parts, I'm not sure how much that would be helpful. I honestly just haven't worked it out. So in this case, what we'll do is we'll make the trigonometric substitution x equals 3 tangent theta. Right? Because this is x squared plus a squared, where in this case 9 is 3 squared. So x equals 3 tangent theta, in which case dx is going to have to be 3 secant squared theta d theta. This now becomes the integral of 1 over, let's see here, the square root of x squared. X squared is going to turn into 9 tangent squared theta. And then there's a plus 9. That's all under a square root. And dx has become 3 secant squared theta d theta. Now once again, this has been rigged so that a trigonometric identity would apply that would make things easier. In our case, we can factor out a 9 from these two terms, and then this now becomes the integral of 1 over the square root of 9 times tangent squared theta plus 1 times 3 secant squared theta d theta. Now then, square root of 9 is, of course, 3, and then that cancels with this 3, so might as well get rid of those. But more importantly, tangent squared theta plus 1 is secant squared theta. So this now becomes the integral of secant squared theta divided by the square root of secant squared theta d theta. And once again, we have a problem where you have a square and under a square root. Those would normally just give you the absolute value. But again, it's not going to matter because once again, we've chosen theta to be greater than negative pi over 2 and less than pi over 2. And over that region, secant theta is always positive, which means its own absolute value, which means the square root of secant squared is just secant. So This is the same as the integral of secant squared theta divided by secant theta d theta, and of course that's just the same as the integral of secant theta d theta. Right then, so you may remember how to do this from the last lecture, I hope. The way that you would need to do this is multiply by secant theta plus tangent theta divided by itself, and then do a u substitution on that, right? We'll just skip to the answer though, because the reason why, I mean, we did that at the beginning of the last lecture, so, you know, it's there. Anyway, this turns into the natural log of secant theta plus tangent theta plus c. Okay. And so once again, we're in this position where, all right, we have some form of the indefinite integral, but we need it in terms of x. So once again, we need to figure out a relationship between these trigonometric functions and the trigonometric function that we are using. Well, first of all, tangent theta is x over 3. So, I mean, that takes care of this one. But secant theta is a little more work. So in order to do that, we're going to have to say, all right, tangent theta, we know that that's x over 3. So let's draw our right triangle. Let's say theta is right there. Now tangent theta is in a right triangle, opposite over adjacent, which means that this opposite side is x and this adjacent side is 3. In that case, the hypotenuse has got to be the square root of x squared plus 9, because that's the Pythagorean theorem. In this case, cosine theta is adjacent over hypotenuse, so that's 3 over the square root of x squared plus 9. And then secant theta is 1 over cosine theta, so secant theta is therefore the square root of x squared plus 9 divided by 3. So that means what we're looking at here can be written as the natural log of the absolute value of, okay, square root of x squared plus 9 divided by 3 plus x over 3 plus c. And that's that. Okay. Hopefully you're starting to get the idea of how these go. I would ask if things are making sense, but you're not going to be able to answer me, so, you know. So let's do one more. At this point you might be thinking, first of all, why haven't we done any definite integrals? And second, do all of these have to involve square roots? The answer to your second question is no, they don't all have to involve square roots, and we'll do an example right now where it does not have a square root. And the other question of why haven't we done definite integrals is, well, first of all, they can get a little bit messy. But more importantly, if you can figure out the indefinite integral, then figuring out the definite integral is just as easy as, you know, plugging in the bounds and then subtracting for the actual indefinite integral. Anyway, in this case, we have the integral from 0 to 1 of 1 divided by x squared plus 1 squared dx. Whoop. Okay. So, in this case, what we're going to do is, again, this is x squared plus 1 squared. So we can say x is equal to 1 times the tangent of theta. In that case, dx becomes secant squared theta d theta. Right? Now, this integrand becomes, let's see here, 1 over, I guess it would be tangent squared theta plus 1 squared times secant squared theta d theta. Okay? Now about the bounds. Well, just as in U substitution, when you do a trigonometric substitution, you can change the bounds. It's a little bit more complicated though. Okay? You see, in this case, when x equals 0, tangent theta is 0. Okay? So then, what is theta when tangent theta is 0? Assuming that theta is greater than negative pi over 2 and less than pi over 2. Of course, the range, again, depends on the substitution. I mentioned that at the beginning of the lecture. But yes, in this range, when do we get tangent of theta to be 0? The answer is when theta is 0. Tangent of 0 happens to be 0. So then in that case, our lower bound is now 0. Okay, so lower bound becomes 0. And I just want to be a little more explicit about that. So x equals 0, that means tangent theta equals 0. And that means theta equals 0. Okay, so this is the logic that I'm going through here to change the lower bound. Now about the upper bound, well, for the upper bound we're saying x equals 1. That's the same as saying tangent theta equals 1. And then tangent theta equals 1, how do you solve that equation? Well, that's the same as saying sine theta over cosine theta equals 1, which in turn is the same as saying sine theta equals cosine theta. The only time that that happens in this range is at pi over 4. So theta has to be pi over 4 in that case. And so our upper bound here becomes pi over 4. Okay? So it's just like U substitution. We're just saying if x is this, then U is that. If x is this, then theta is that, whatever. But as you can see, it's just a little bit more, complicated just because it has trig in it. Right then, so now, we have secant squared right here. Tangent squared plus 1 is secant squared. So this becomes the integral from 0 to pi over 4 of 1 over secant squared theta squared times secant squared theta d theta. Now, of course, secant squared divided by secant squared squared is 1 over secant squared. So this is the integral from 0 to pi over 4 of 1 over secant squared theta d theta, which, as we know, secant theta is just the same as 1 over cosine theta. So that means that this is the same as integral from 0 to pi over 4 of cosine squared theta d theta. Oh, we actually already dealt with that today, didn't we? Yes, this is, once again, just the integral from 0 to pi over 4 of 1/2 1 plus the cosine of 2 theta d theta. We pulled the 1/2 out because it's a constant. And then we do this antiderivative. This antiderivative becomes 1/2, let's see here, theta plus, I suppose this would be 1/2 sine of 2 theta. And all of this is evaluated from 0 to pi over 4. Okay? So we plug in the bounds, and what we get is, this is 1/2 times pi over 4 plus 1/2 times the sine of 2 times pi over 4 minus 1/2 0 plus 1/2 times sine of 2 times 0. Now, sine of 0 is 0. 0 plus 0 is 0, so all of this can just be ignored. What's important is that the sine of pi over 2 is 1. So this is pi over 4 plus 1/2, and then this just becomes 1/2 times pi over 4 plus 1/2, which I guess turns into pi plus 2 over 8. Anyway, that's our definite integral. Now, you might notice there's no triangle here. That's because we changed the bounds. Okay? Just like in U substitution, you can choose to not change the bounds and put everything back in terms of x and then apply the original bounds. That is valid. I wouldn't recommend it. I prefer to do this, honestly. But it is possible. Okay. All right, so that's it for today's lecture. Homework is up, so go ahead and get some practice on that.